So vector functions. What's our independent variable or thing, and what's our dependent variable or thing, and how do they graph? So we should know that. So if we're going to do all these problems about vector functions, before any problems that we do, we know the basis of vector functions. What goes in, what comes out, what does it give us, and how do we represent it graphically? So what goes in? A vector? It's a vector function. So a vector goes in, right? Takes vectors, right? No, tell me. Scalar, right? That's what t is. It's a real number. So it starts with a set of real numbers, and for every one of those real numbers, you get a vector, right? So it's a set of real numbers that maps to or gives corresponding vectors, right? That's a vector function. And how do we imagine the graph of that? Surface? It's a surface. No. A line. That's one example. A line is a specific example of what we can get, but in general, a curve, right? So we put all those vectors in standard position, and we let that scalar increase, and we get all those vectors in standard position, and it's like a laser light show, right? The tips of those vectors then sweep out a curve in space if it's R3, or in the plane if it's R2. So the graph is a curve, or a string of points, not a curve, it's a curve. Yeah, so a string of points drawn out by the tips of all those vectors that we get as the dependent variable. Okay, and those are of the form what? That scalar goes in, and then what comes out is a vector. Each component is a function of the scalar. In contrast to equations of x, y, and z. That's something we've also seen. So a single equation that brings together x, y, and z. So those are not functions, but how do those graph? Surfaces, right? We get surfaces. When you have an equation of x, y, and z, you're talking about all ordered triples that make that equation true. You'll get a surface, right? So plane, what are the surfaces that were our basic surfaces we've talked about? So someone said plane. What else? Sphere. What else? Cones and double cones, right? What else? Hyperboloids, although we didn't, that's a, what else? Cylinders, right? You did your little 10-minute video before the tests. Cylinders. Take any curve and just extend it, a curve in a plane, extend it orthogonal to the plane, it sweeps out a cylinder, right? There's one more big one. What's that? Paraboloids, right? Paraboloids. These are the big ones that we need to know. Cylinders, planes, spheres, paraboloids, double cones, and ellipsoids, right? Ellipsoids. All those things are equations of x, y, and z. And so they give you surfaces in space, whereas vector functions give you curves in space. Okay, so what happens when two surfaces intersect? So here we've got a sphere, and we intersect it with a plane, minus y equals 3. So there's some sphere here. And we come along with a plane. This. What do you get then when you intersect the two surfaces together? Well, not just in general, any two surfaces. You get a curve, right? Is that what you're saying? Yeah, you get a curve. And how do we represent curves? How do we? Yeah, vector function, right? So take two surfaces, they're going to cut, and they're going to create a curve. So based on the equations of those two surfaces, we should be able to generate then a vector function that is that curve. Does that make sense? All right, so for this one, we've got y equals 3. Here's y equals 3. and this sphere, x squared plus y squared plus z squared equals 73. So we need to do some math with those two, right? We're intersecting, so we're going to bring those equations together. When we bring those equations together, then we should be able to write, based on what we get, we should be able to write a vector function that is the points of that curve. Okay? So how do we bring these together? It's an easy one, right? Y equals 3 and this. So then that, combining those two together, we get what? X squared plus 3 squared, 73. So therefore, x squared plus z squared equals, is that 64? Well, lo and behold, it's right, right? Okay, and so what's that? X squared plus z squared equals 64. Circle of radius 8. Okay, and then so that will be it'll be this circle that you get when you slice down vertically at y equals 3. In the plane y equals 3, okay? So now we're going to write so we've got this curve, we want to write a vector function for that. So r of t. And there's two basic techniques that you need to know. The first technique is when you have circles and ellipses projected into one of the coordinate planes, like if you take away one of the variables and the remaining two gives you a plane or a circle or an ellipse, then what's our strategy for that? What are we going to use? Cosine and sine, right? So do we have that here? Yeah, we've got this circle. That's the shadow of the circle is in the xz plane, and that's certainly our circle right there. So we're going to use cosine and sine of x and z to do that. So we can say x equals, so what's the radius of our circle? 8. So we can say 8 cosine t for x and 8 sine t for y, z, I mean. And then what's left for y? Every point on that circle has a y coordinate of 3, so it's always 3. So that's the first kind of approach. If you have, in one of your views of it, at least one of your views, if you have a circle or ellipse, then you're going to use cosine and sine. The other situation is the next example we'll do. Okay, so we'll do the next example. So any questions about this example? Or just vector functions and surfaces in general? So combine the two equations of the surfaces, and you have the information you need then to generate a vector function for that curve of intersection. Okay, so let's look at another example. Can I erase what's on the screen? I think I want to do this one. No, I do not want to do this one. I want to do this one. Okay, so I have this surface z equals square root of x squared plus y squared, and z equals 1 plus y. So first we need to identify and sketch those. So z equals square root of x squared plus y squared. So let's I'll just have you do that. So why don't you, I'll take attendance, identify these two surfaces and try to sketch them, and then try to sketch the curve of intersection before doing any math, right? Don't do any math yet. Just sketch the surfaces, try to figure out what the curve of intersection will look like. And then take time to think, but also talk amongst yourselves. Talk amongst yourselves. Work together. What is that? Paraboloid. Is it a paraboloid? It's a paraboloid without the square root. Z equals x squared plus y squared is our paraboloid. So if it's z equals square root x squared plus y squared? Cone. Double cone? Single, just the positive, right? So if you squared both sides, And then to the square root again, you'd have plus or minus, right? The plus being up, so it's the single cone opening up. Let's turn that on. Okay. And z equals 1 plus y. What's that? Okay, I heard a line and a cylinder. Okay, put those two together, and what do you get? It's a cylindrical line. What is that? Plane, right? That's a plane. It's a cylindrical. It's true. It's a linear cylinder, right? It's a linear cylinder. So that's a plane, right? So we just don't have an x term here. So it's a plane that's what, parallel to the x-axis. And so so depending on the inclination of the plane is going to determine what we get when these intersect. So the sides of our cone are linear at what, like at a constant rate, like it's a 45-degree angle. So is our plane. So what will we get when they intersect? Yeah, we're going to get a parabola. So let's try yellow here. No, I don't want yellow. Let's try. Okay, see that? So that because the angle of that plane is the same as the angle as the side of the cone, you're going to get a parabola. Do you see that? So are we going to use cosine and sine then? I'm not going to use cosine and sine because the intersection, let's try a little brighter. Like that. That's a little better, I guess. Oh, that's good. That's good. All right. So we're not going to use cosine and sine because our intersection isn't circle or ellipse. Okay. So let's take a look at what we do then. So what's kind of a good strategy for? Yeah. So we got z equals and z equals. So here we can just start by saying just set the z's. Or substitute 1 plus y in for this z because it's equal to z, right? So 1 plus y. So just a side note, you don't set equations equal to each other. So students say that all the time. So we're combining the equations, right? There's different ways to combine equations, but you never take two equations and set them equal. Okay? So here I'm taking, since they're both equal to z, then they're equal to each other, right? So 1 plus y equals that. All right, first step, get rid of the square root. And then over here we can expand the binomial square. And that's nice because then y squareds go away. And I can solve for y. So what is y? Y is going to be x squared plus x squared minus 1 all over 2. So, and what is that? So now I've got an equation of x and y, and what kind of equation is it? Parabola. And so again, that's the face of this curve, this intersection, this curve. That's the face of it in the xy projection, right? So that's my parabola. So now I have to parameterize that, right? I have to get that in terms of t. So here's the kind of the second technique that you use, and that's if you have one variable in terms of the other, then just set that kind of that independent variable equal to t. So before we had like x and y were in a circle or an ellipse, then we use cosine and sine. But now if you can get y equals a function of x or x equals a function of z or something like that, then you can just set that independent variable equal to t. So in this case, x is t. And then what is y if x is t? Over 2. And then what is z? Well, z is, you can use either one, but there's a much better choice than the other. 1 plus y. So then what is z? 1 plus y, which is t squared minus 1 over 2. And if you simplify that, if you do the math, t squared plus 1 over 2. So there's our vector function. So if we put that in and turn it on, we should get, so what was, we're going to say, okay, touchy. So t and t squared minus 1 all over 2 and t squared plus 1 over 2. So is that the vector function we came up with? So if I turn that on, let's make it something dark, like dark blue. Turn that on. Too big. So did we get it? So now that's, I'm graphing that, what we came up with in dark blue. Did we get it? Yep. So there it is. So that's the vector function t squared minus 1 over 2, t squared plus 1 over 2. And that's came from bringing those two surface equations together. So therefore, it's all the points on both surfaces. All right, so let's see, let's try a different example. Any questions on this one? So if that, say if this was, so what if that plane had a shallower angle? It didn't have the same angle as the side of the cone. Then what are we going to get? Yep. So I got to turn off my. So now look. So here you get an ellipse. So when you start forming your vector function, you're going to use the other technique where you're going to pick two variables to be cosine and sine, and then you got to do the math. So let's see a different example of that. All right, so why don't you, here's two cylinders. So try sketching these and see if you can just conceive what the intersection, do your best to draw it. It's a little trickier, but if you can just imagine it and do your best at a drawing of what the intersection of these two cylinders would be. X squared plus y squared equals 16, z equals 0.5 x squared.
Like the center part, like chocolate.
So that's the first cylinder, right? Let's try yellow. So that, no. Everything's so dark in this, they need to replace the lamp. So can you see? Try purple. There we go, that's better. So do you see the curve of intersection? It's kind of like a circle that's wavy up and down, like the edge of a Pringle, a distorted Pringle kind of. You know what Pringles are? You're laughing because, of course, you know what Pringles are?
They still sell them.
They still sell them, yeah. They're not just from the 60s, like when I grew up. I didn't grow up that long ago. All right. Okay. All right, so we want to write the equation of that crazy curve. So we're going to combine these equations. How do we combine these equations? What should we do?
Solve for x.
Solve for x, okay.
Isolator above.
Well, so actually, we can just start off, we've got x squared plus y squared equals 16. So we can just start with that. We don't have to, we can just get going without combining them because we already have an equation of two variables. So just from that alone, we can start writing it. You see? So what would we write it as? 4 cosine t and 4 sine t. Because that now has the right relationship of x and y, right? And then z is what? 1/2 of x squared. Well, but this is x, right? It would be 2, what? Well, 1, so let's do the math here. It's going to be 1/2 of 4 cosine t squared. So that's 16. Is it 8 cosine squared? So we already have x squared plus y squared equals 16. So we can write down 4 cosine t, 4 sine t for x and y, and then z is according to this relationship with x. So it'd be 1/2 of what we said with x squared, which is 1/2 of quantity 4 cosine squared, which is 8 cosine squared t. So again, if I put that in as a vector function, it should show up as the intersection. Here's 4 cosine t, 4 sine t, 8 cosine squared. So let's make it, I don't know, turquoise. Let's see if turquoise shows up. Kind of. It's dark. See it? So that's that turquoise curve is the intersection of those two, and it's the function we said: 4 cosine, 4 sine, 8 cosine squared. So if we look in the xy plane, what do we see? Circle. X squared plus y squared equals 16, taking away z. If we take away y and look at the xz plane, what do we have? Which parabola? One half x squared, right? Z equals 1/2 x squared. There it is. So then looking at just x and y, y and z. Looking right down the x-axis at y and z, we could do some math and we'd get the parabola that's being shown there, right? That's another parabola on y and z. Combine 4 sine t and 8 cosine squared, use trig identities, and you can get this parabola. Okay, questions on parameterizing or using vector functions for intersections of surfaces? Maybe we'll do one more. So that the web work will be due late again on Friday. Maybe we'll do one more beginning of class Friday. Okay, so then we want to go look back at our vector functions and take a different route here. The questions on these. So back to my favorite vector function. Where is it? Here it is. X is cosine t, y is this quartic polynomial, and z is half sine 5t. And so if you let let t increase, you get this set of vectors which sweeps out this curve. So I'm showing t from -1 to about 4, I think. So this is t increasing from -1 to 4, and all the vectors you get sweeping out the curve. So now I want to show you another vector in this animation. This blue one, okay? And I'm going to put its tail at the tip of the original vector function. So I want you to just have a little conversation, and I want you to make observations about this vector, its magnitude and its direction. So that's how we talk about vectors, right? All vectors have magnitude and direction. So as you notice the curve being swept out, what can you say about this new vector that I've added into the animation here? So go, have a conversation. So this new vector I've added into the mix here. So let's first talk about the direction of that vector. So Christian, what do you notice about the direction of that vector? Is it orthogonal? Orthogonal to what?
The slope at every point, or it is the slope of the.
Oh, I said Christian. Sorry.
Oh,
Yeah.
yeah.
It's okay.
It's the rate of the direction of the rate of change, like how it's varying across, like to get to the next point.
So,
It's
like,
pointing
what's its direction relative to the curve? So, like, the curve that's being swept out, what's the direction of that relative to the curve?
It's pointing towards where the next points are going to be.
Right. Yes. It's like it is the direction of the curve at that moment, right? Do you see that? It's pointing exactly to the next point. It's like you said. It's pointing right at the very next point, or currently how it's going. Okay. All right. Good. So it's like pointing out the direction of the curve, and then what do you notice about the magnitude? Jonas.
It changes in magnitude as how far the points are moving. So as t moves at constant rate, sometimes the arrow moves faster or slower depending on how fast the curve is moving.
Okay, so yeah, so it's like its magnitude is kind of showing like the rate at which the points are being swept out. Do you see that? So when there's very few points being swept out for changing t, it's short. But now for the same change in t here in the back, you get lots of points being swept out for the same change in t, and so then that vector is a lot longer, right? So this would all sound like a very important calculus concept. We're pointing in the direction of the curve, and its magnitude of that vector is like the rate at which the curves are being the points are being swept out relative to t. So what is that? It's derivative, right? And so this is what I'm showing you now. This set of vectors, this new set of vectors, is the derivative of the vector function. And lucky for you, it's exactly what you think it should be. It's like the easiest possible thing that you would want it to be. How will we get that function? Yeah, right. So we're going to take the rate of change with respect to x, the rate of change of x with respect to t, the rate of change of y with respect to t, and the rate of change of z with respect to t. So what is it? Negative sine t. 4t cubed minus 12t squared minus 6t and minus 6t. And then this will be, what, 5/2 cosine 5t, by the chain rule, right? So this new set of vectors that I'm showing you, for every given t, these blue, it looks blue some of the time, is this vector function. Now notice how I'm graphing it. For the original vector function, what did we do? We took all the vectors and we graphed them in standard position, and it swept out the curve. For this one, it makes a lot more sense because of what it is to put all the set of vectors at the corresponding tip of the original vector function. So we could graph this with all the vectors in standard position and draw out a new curve, but then it doesn't reflect what we want it to reflect about the curve the way that this does. Does that make sense? So I'm gonna put all those vectors rather than in standard position like we did for this one. I'm gonna put all those vectors with their tails at the tips of these vectors for corresponding t, and that's exactly what I'm showing. Okay, that's called a vector derivative function. Okay, how about something new? Okay, talk. What am I showing now? Let's see if you can figure this out. What am I showing now? Edis, what do you think?
I'm not sure. It looks almost the same, but
Almost the same. What's the same? What is the same?
well, the curve is drawing the same curve.
So the original function is drawing the curve.
Yeah, but the
So this, what is it about this new vector set of vectors that's the same as this one?
yeah,
Direction is the same, right? The direction is the same. But then what about the magnitude now? It's staying constant, right? It's staying constant. So some people are guessing that it might be. Maybe that constant is a constant length of 1. All right? And so, yes, that's what that is. So this is what this is supposed to be showing. Is that we have the same direction, but with a constant magnitude of 1, no matter how the curve is being swept out relative to t. So I want you to write that function. Write this new function. Can you write it? Same direction as this, but all the vectors now have magnitude 1. Can you write that function?
The vector derivative function that we have divided by the magnitude of that vector, which is the x, y, and z, each like squared and added.
Right. So you're going to take this function, and you're going to divide it by, or scale it by 1 over the square root of the sum of the squares. So let's use function notation to make our life really easy. So let's just do that with this side. Well, what would it be? The function, right? Then what? Divided by magnitude of that. Did anyone do that? That would have been right if you did that. Did you do that? Good. Good. Okay, this is called, so this is the original vector function. This is the original vector function. This is called the vector derivative function. And this is called the unit tangent function. Because it gives a set of unit tangent vectors, right? Each of those vectors is a unit vector that's tangent to the function or points in the direction that the function's being swept out. So we use capital T for that. So capital T is the unit tangent function. It gives a set of unit tangent vectors. So I can pause life here. And now here t is 0.61. And so now you can write that vector if t is 0.61, right? That would be this is the vector t of 0.61. And if you really needed to get that, what would you do? You'd find the value of the derivative function, derivative vector, divide by the magnitude, all of that when little t is 0.61. That would give you 3 numerical components, an x component, a y component, and a z component would be this particular vector. take all those vectors for all t's, and that's the unit tangent function, right? That's what I'm showing you when I start the animation again. Make sense? Okay, so we're just rolling one web work every class. Oh, and then you have recitation tomorrow. You get your next set of problems to work on.